Okay, looking at the car and the magnet and so forth. Um, first of all, we want to look at a graph of the net force on a coasting cart if there's no magnet. Now, the car is coasting along a constant incline. And let's assume a level incline so that as the car coasts, it's subject to the force of friction in the direction opposite motion. In that case, your net force is going to be this purple, represented by this purple horizontal line. The net force is going to be constant. Now, there's some confusion because people tend to think, well, let's see, the car's slowing down, so the net force must be slowing down, or somehow the acceleration's changing. Well, you want to analyze that a little bit. So we do a free body diagram. We have mg, force of gravity acting downward, Fn, the normal force, which is acting upward, and you have the frictional force acting in the direction opposite motion. Now, the frictional force is not nearly this big, but I had to draw something. To draw it realistically, it would only be very, very tiny. It would be difficult to see. So this is kind of a schematic diagram showing where the forces are. Well, we know that the normal force and the gravitational force are in equilibrium because they're vertical and the car is moving on a horizontal. It's not moving in the vertical direction, so it's not accelerating in the vertical direction. Okay, so these two forces are in equilibrium so that this force here is equal and opposite to this. So the magnitudes of the two forces, the gravitational force and the normal force, are equal. The vector forces are equal and opposite. Now, we have to analyze where's the force of friction come from. Well, the force of friction is a response to the normal force, okay? And it's equal to the coefficient of friction times the normal force. We assume that the coefficient of friction is constant. It's not quite true, but we assume that it is, and it's close enough for most applications. So force of friction is the coefficient of moving friction times the normal force. UK, that's actually rolling friction in this case. We might use a mu sub r for that, but I think your book just uses a mu sub k and a mu sub s. I could be wrong. So I use mu sub k just so as not to confuse the notation, but that is a rolling friction. Now, we actually made an estimate of the coefficient of rolling friction by just estimating how long it takes the car to come to rest after we poke it. It goes maybe this far in a couple of seconds, and we can then estimate the acceleration. Okay? And we get an acceleration that turns out to be about, what we got was about 20 centimeters per second squared. I didn't fudge that, but that turns out to be pretty much what you get for a set of good wheels with good bearings. And it doesn't really matter if it's the Hot Wheels car or your car going down the road. The rolling friction tends to run around 2%. It can be lowered by adjusting tire pressure and surface and stuff like that, but not all that much. Okay, now steel wheels on a steel track, much lower coefficient of friction. Rolling friction is about 1/10 of this. Okay, just a little bit about rolling friction. That's kind of a digression, but it's part of what's going on here. So, from the fact that m and g are constant, well, we conclude that mg, the weight of the cart, is constant. And since the normal force equals mg, the normal force is constant. So the frictional force, which equals coefficient of friction times the normal force, coefficient of friction we assume is constant, the frictional force is constant. So the net force, which in the absence of the magnet, because we specify no magnet here, in the absence of the magnet, the net force is the frictional force, because you only have three forces, and two of them are in equilibrium. You're just left with the third one. Okay, so we have we draw the conclusion that the frictional force is constant, which is why then this line is horizontal. Now why does the line suddenly jog up here? Because the car comes to a stop. When the car comes to a stop, there's no more rolling friction. There's zero force in the horizontal direction, and there are no other forces acting. So the total net force has got to be the frictional force, and since it's zero, the frictional force is zero. And of course we know that frictional force depends on relative motion of two surfaces. Okay. Uh-oh. I'm trying to get this thing to behave, but it's being resistant. Okay. Now, let's look at the force from the magnet. Now, we haven't measured the magnetic force. We will do that sort of thing, but right now, we don't know what the magnetic force is. We don't know how it behaves. I've got a little better idea than you have because I've measured it, but it's pretty complicated, okay? And we can always model it using multivariable calculus as a series of parallel dipoles that make up the ceramic magnet, and that works a little better, but it's not perfect, and that's beyond the scope of this course anyway. So it can be modeled, it can be measured, but it basically has a characteristic like this. It actually drops off a lot faster and then more and more slowly, and presumably the magnetic force theoretically goes on to infinity, but it drops off very rapidly and very quickly becomes negligible. Now, it's not totally negligible at the distance the car moves. When the car moves a pretty long distance, it pretty much becomes negligible. But if you just have a run about this long, there's still a magnetic force of some significance. Okay, so that's what the magnet force looks like. And at some point the car stops. So you have a non-zero magnetic force when the car stops. Okay, now if we then do the net force, because the net force, if I expand this diagram a little bit, you're going to have a magnetic force in this direction that decreases with your distance from the magnet. You're going to have some magnetic force. So you're going to have frictional force this way and a magnetic force pushing you that way. Well, if the white curve represents the magnetic force that we see here, and the purple curve or the purple broken line represents the frictional force, and the frictional force, of course, comes to zero when the cart stops, then the red graph is going to represent the net force. And actually, I was a little careless at the end here. The net force becomes asymptotic to this non-zero frictional force. When that non-zero frictional force ceases, the frictional force goes back up and joins, the frictional force becomes zero, and the net force goes back up and joins the magnet force curve. Now at that point, you actually have a force of static friction that still brings the net force back to zero. So when I drew that, I was being careless. It really becomes zero at this point. Because of course the car is stationary. And I should probably go ahead and, gosh darn it, fix that graph. Okay, so what I said a minute ago, the magnet force doesn't, the frictional force, sorry, the net force doesn't join the magnetic force. There's actually a little bit of frictional force because of the static friction in response to the magnetic force. So it's like we got some static friction now. And that approaches zero. I didn't draw that line very straight, but you get the idea. That approaches zero along with the magnetic force. And okay. So what we have is this net force. You have a regime here, an interval of the position axis, where the net force is positive. This is where the magnetic force exceeds the frictional force in magnitude. When the two become equal in magnitude, they cancel each other, and your net force is zero. The cart keeps moving. But now the magnetic force is less than the frictional force, so your net force is negative. So when the net force is positive, you have a decreasing positive acceleration. Decreasing because the magnetic force is decreasing, but positive because the magnetic force is greater than the frictional force. On this regime, you have an increasing deceleration. I don't like the word deceleration, I like negative acceleration, but in this case I think deceleration is probably a better word. So you have an increasing deceleration because why? Because the magnetic force is decreasing, but the frictional force of the rolling friction is not decreasing. Now, at this point, everything stops, so we're not even really interested in what happens beyond here, but it's still a good illustration. It's something we want to talk about. So when the cart is sitting there with the magnet still present, you have a little bit of magnetic force and a little bit of frictional, static friction opposing the magnetic. That's here. Okay, not particularly interested in that right now though. Okay, so up to here, this is what your net force looks like. So here's another picture of what the net force might look like, and it's maybe more realistic because the magnet force decreases pretty rapidly, and it doesn't take long before the net force is zero and then goes negative. So you get a lot of magnetic force for a short time, and then a little bit of frictional force for a longer time, or more properly, significant stronger magnetic force for a short distance, and then a weaker frictional force for a much longer distance. And that's the way the net force works. Now, the graph of acceleration versus position and that was really kind of ignorant. Okay, position changing with respect to time. So, your acceleration versus time is not going to look exactly like this graph. It's still going to have the same characteristics. It's still going to be zero when the net force is zero, but that's going to occur at some time. If you integrate this curve with respect to time, the area of this part is going to end up being equal I should have never called that acceleration versus time, because I'm really going to talk about energy, not impulse and stuff. So this, I'm going to change this back to position. I'm going to change this back to net force so that I can say what I said earlier. I was trying to make a connection between the force and acceleration, and I did that without thinking very much. Okay, so here's your net force, here's your position. The velocity at this position is equal to the area of the curve between here and here, the area of this portion of the curve. Why is that? Because, as you know, okay, I said that wrong. It's not the velocity. This is a kinetic energy. When you integrate force with respect to position, you get the change in kinetic energy. Kinetic energy is here. So this is kinetic energy, and every velocity I talk about here is a kinetic energy, and that's a really fundamental distinction. I'd say I can't believe I did that, but yeah, I can believe I did that. So I'm going to stop at this point and correct this, okay, because this is all in a way correct, but when I'm talking velocity, I need to be talking kinetic energy.